We all tend to think of the ground beneath our feet as, well, solid rock, immovable. But what if it's not? What if, in certain places, the Earth itself is sinking, compacting almost like a giant sponge? This isn't just some weird little curiosity. It's a huge geological mystery with billion-dollar consequences. So today, let's dig in and uncover the hidden science of how rock can actually flow. So here's the central puzzle we're trying to solve. Why is the ground physically sinking over some of the world's biggest oil fields? And we're not talking about a few inches here. We're talking about the surface dropping by several meters. This isn't a random thing. It's a massive clue that something really profound is happening thousands of feet below us, deep inside the reservoir rock itself. To crack this case, we're going to zoom in on one specific place, the Wilmington oil field in California. Now, the rock here isn't the solid, sturdy sandstone you might be picturing. Geologists actually call it uncemented sand. And that's pretty much what it sounds like. Loose, weak sand that's been buried about a kilometer deep. And that weakness? That is our first major clue. Okay, before we can really understand this strange, weak sand, we need to get a baseline. We need to know what normal looks like. So first up, let's take a look at how a typical, strong rock is supposed to behave under pressure. This is going to really highlight just how bizarre that Wilmington sand truly is. So this classic behavior is called linear elasticity. And honestly, the best way to think about it is with a simple spring, right? You squeeze it, it compresses. You let go, it bounces right back to its original shape. For a material that's perfectly elastic, the amount it deforms, which scientists call strain, is directly tied to the force you apply, the stress. It's super predictable, and most importantly, it's completely reversible. But here's the thing about the real world. Even a strong rock isn't a perfect spring. When you first start squeezing a real piece of sandstone, you see its response isn't a perfectly straight line. What's happening there? Well, that's just tiny, pre-existing microcracks closing up. After that initial squish, yeah, it acts pretty much like a spring. But if you push it too hard, you'll actually cause permanent damage before it finally breaks. So you see, even the simple case has its own hidden complexities. Okay, so we've got our baseline for a simple, dry rock. But the sand at Wilmington is anything but simple. In a real oil reservoir, we have to add 3 new, really important ingredients to the mix. Fluids, like oil and water, immense pressure, and the biggest factor of all, time. We're talking decades and decades of. First complication is something called poroelasticity. Just imagine a wet sponge. If you squeeze it really, really fast, the water can't get out in time, right? It pushes back, making the sponge feel stiff. That's what's known as an undrained response. But if you squeeze it slowly, the water has time to drain out, and the sponge compresses super easily. That's drained. The exact same thing happens in rocks, and it means the rate at which you change the pressure is incredibly important. This brings us to a really crucial idea called effective stress. Try to picture the rock grains deep underground. They aren't holding up the entire weight of the Earth all by themselves. The fluid in all the tiny pores between the grains is also under pressure, and it's pushing back, helping to support some of that massive load. But what happens when we pump oil out? Well, that fluid pressure drops, and all of a sudden the rock's solid skeleton has to carry way more of the weight. This increased load is the effective stress, and that's what's causing the rock to get squeezed. And now, for the final and maybe the strangest piece of our puzzle, viscoelasticity. A much better name for it, though, is just creep. The absolute best way to think about this is with silly putty. You can roll it into a ball and bounce it just like a solid. But if you leave it on a table, it slowly flows into a puddle, like a liquid. That is exactly what this uncemented sand does. Under a constant load, it doesn't just compress and stop. It keeps slowly, inexorably deforming over time. It creeps. So now that we have all these concepts, how in the world do scientists actually measure this stuff and predict what's going to happen over 30 years? I mean, you can't just sit and watch an oil field for 3 decades, right? The answer is you bring a piece of the oil field into the lab and you design some incredibly clever experiments. So here's what the experiment looks like. They take a core sample of that Wilmington sand, they stick it in a special pressure vessel, and they slowly ramp up the pressure in steps. Then, after each step up, they just hold the pressure steady, and they watch. And what happens is incredible. The rock sample continues to shrink and deform, all on its own. That slow deformation while the pressure is constant, that's the creep we've been looking for. And this is exactly why that experiment is so critical. This quote says it all. If you only measured that initial springy compression and you completely ignored the slow creep that comes after, your prediction for how much the ground will sink would be dramatically, catastrophically wrong. You'd literally be missing half the story. And this chart from the lab results just tells the whole story perfectly. See that first bar? That's the immediate, instantaneous strain. That's the elastic part, the springy part. But then look at the second bar. Over the next few hours, the rock continues to deform, and that creep strain is just as large as the initial squeeze. That's kind of mind-blowing when you think about it. The slow flow is just as important as the initial compression. So what's causing this creepy behavior? Well, it's not the strong quartz grains, the actual sand. Experiments show that if you test pure, clean quartz sand, it barely creeps at all. The real culprits are the weaker minerals that are mixed in, specifically things like clay and mica. These soft minerals basically act like a lubricant, allowing the stronger quartz grains to slide past each other and rearrange themselves over time. And that's what causes the whole rock to compact. Okay, so we can measure creep over a few hours in a lab. Great. But this raises the biggest challenge of all. How do you take a few hours of data and then confidently use it to predict what's going to happen over the entire 30-year lifespan of an oil field? I mean, that is a massive, massive leap in timescales. Well, the solution was to find the perfect mathematical model that describes this behavior. And here's the really clever part. The researchers found that several different models could be tweaked to fit their short-term lab data, but only one of them, something called a power law model, also perfectly matched other known properties of the rock. It was the only model that worked from all angles, which gave them the confidence that they had found the true physical law that governs how this rock behaves over time. So we've gone from a real-world problem to the lab. We've waded through some complex physics, and we've even gotten into mathematical modeling. Now, let's bring it all back home and see how this science provides a real solution and why it has such a huge impact. And here is the big payoff. Using their lab data and that power law model, scientists made a bold prediction. They said the reservoir would compact by about 1.5% over 30 years. So, what did the real-world data actually show? Well, by measuring how much the steel casings of the wells were literally crushed over the decades, they found the actual compaction was about 2%. That is a spectacularly close match. It's just a powerful validation of the entire scientific process. So why does all this matter so much? Because with this knowledge, engineers can now accurately predict how much the ground is going to sink. They can manage the oil flow better, they can mitigate risks from earthquakes, and they can design wells that won't get crushed by the immense pressure. It basically transforms oil extraction from a bit of a guessing game into a predictive science. And so we end right back where we began, but with a completely new perspective. The ground beneath us isn't always solid. With enough pressure and enough time, rock itself can flow. Which leaves us with one final, fascinating question to chew on. What other secrets is the solid earth hiding right under our feet?